Good day, everyone, and especially to our chief engineer instructor. Thank you for joining me. Today, we're going to dive into the core of thermal power plant performance by focusing on the calculating steam turbine efficiency. This isn't just a number, it's the definitive measure of how effectively we convert fuel into useful power. The workhorse of power generation function converts the thermal energy of high pressure and high temperature steam into mechanical work. Ideal process. An ideal steam turbine process is isentropic, meaning it is reversible and adiabatic. Actual process. In reality, friction, turbulence, and heat loss make the process irreversible, leading to lower than ideal work output. Key operating parameters. Inlet steam condition. Pressure 1 or P1, temperature or T1, enthalpy or H1, entropy or S1, outlet steam condition, pressure or P2, temperature or T2, enthalpy or H2, entropy or S2, steam flow rate. A steam turbine is a workhorse of any thermal power plant. Its sole purpose is to convert the thermal energy or enthalpy in superheated steam into mechanical rotation. We start with the ideal process, which is a which is a perfect and isentropic expansion, meaning constant entropy and no losses. Unfortunately, in reality, friction and turbulence make the actual process irreversible. To perform the calculation, we must accurately measure 4K operating parameters at the turbine's inlet and outlet. The pressure RP1, temperature RT, which is allow us to determine the enthalpy RH and entropy RS. The energy budget of turbine. The entire analysis is governed by the first law of thermodynamics, which is the principle of conservation of energy. Simply put, energy cannot be created or destroyed. It only converted. To analyze this, we treat the turbine itself as a control volume. We make two simplifying assumptions. First, it operates at a steady state, meaning a flow condition don't change over time. Second, it is adiabatic. This means we assume there is no significant heat loss from the turbine casing to the surroundings. Therefore, all the energy conversion happens inside the turbine. The basic function of turbine is to convert the thermal energy carried by the high pressure steam into mechanical work. The slide states that the work output, the mechanical power generated, is equal to the change in enthalpy of steam. Enthalpy is essential to to the total energy content of the steam as the steam expands and pushes the turbine blades. It gives up its energy. This lost energy is precisely the work we extract. K variables. Inlet enthalpy. This is the high energy of steam entering the turbine high pressure and high temperature. Outlet enthalpy. This is the lower energy of steam leaving the turbine lower pressure or lower temperature. Mass flow rate. This is how much the steam is flowing through the turbine per unit of time. The faster we flow steam, the more total energy is available for conversion. Measuring operating parameters. Inlet pressure P1 before stop or control bulbs define available energy, and let temperature T1 before stop or control bulbs define available energy, exhaust pressure P2 at turbine outlet or condenser define the expansion limit, exhaust temperature T2 at turbine outlet determines actual outlet enthalpy or H2, flow rate M or main streamline flow meter used for power calculation. When we talk about efficiency in a power plant, we often encounter two terms. Thermal efficiency compares the overall work of the entire cycle to the heat added in the boiler. It's the measure of the overall plant's fuel economy. However, our focus today is isentropic efficiency. This metric is solely sol- solely this metric is solely concerned with the internal performance of the turbine component itself. It compares the work the turbine actually actually produced to the maximum possible work it could have produced under ideal condition. Defining efficiency NISO versus NTH. Two ways to measure performance is entropic efficiency. Measure the quality of the turbine expansion process itself. Ratio of actual work to ideal work. 2. Thermal efficiency. Measure the overall effectiveness of the entire Rankine power cycle. Ratio of power net output to heat input from fuel. We use NISO to monitor the turbine component health. The benchmark is entropic expansion, which is the ideal theoretical maximum work we could possibly extract from the turbine. An isentropic process means entropy or S remains constant. S1 equal S2. This gives us the gold standard for comparison. The ideal work or W ideal is calculated using the ideal change the enthalpy H1 dash H2. The key term is H2S, which is the theoretical exhaust enthalpy under perfectly lossless conditions at the measured exit pressure. The difference between the actual work output and this W ideal represent the energy loss due to irreversibilities like friction and turbulence inside the machine. And the isentropic efficiency equation. This W ideal or work ideal serve as the crucial denominator, the maximum potential work against which the compare to our real world performance. The isentropic efficiency formula. Isentropic efficiency is calculated as a simple ratio, actual work output divided by the ideal isentropic work output. The ideal work is defined by maximum energy drop H1 or H2. Possible if the steam expansion were perfectly isentropic, since the mass flow rate is the same both for the denominator. It cancels out. We are left with the final and most critical formula. The ratio of the actual enthalpy drop H1 and H2 to the ideal enthalpy drop Actual enthalpy drop H1 dash H2, H1 and H2 to the ideal enthalpy drop H1 and H2S. Step-by-step calculation. Step 1 and Step 2 are direct. We use the measure pressure and temperature at the inlet and actual outlet to find H1 and H2. The crucial thermodynamic step is Step 3. Find the isentropic outlet enthalpy. H2S. For this, we use the actual outlet pressure RP2, but we pair it with the inlet entropy RS1 because entropy remains constant in the ideal scenario. Once these three enthalpies are derived, step 4 is a simple plug and chug calculation. Interpreting efficiency values. Typical efficiencies. A large utility turbines often 85 to 92%. Performance degradation. A sudden drop in NISO alert operators to problems. Fouling. Deposits on blades restrict flow and create turbulence. Erosion. Wear on blades changes aerodynamic profile. Internal leakage. Increased clearance between rotating and stationary parts. Economic impact. Even a 1% drop in ISO and a large plant result $1 million of lost power generation and increased fuel consumption, heat rate. A large industrial turbine typically operates between 75 and 90% isentropic efficiency. This value is a vital performance monitoring tool. Any gradual drop signal a problem. Blade fouling. Deposit on the blades. Increased clearance, steam leakage past the seals. Or general wear. Most importantly, efficiency direct impact the heat rate or HR. A lower NISO results a higher heat rate, meaning the plant must burn more fuel, produce the same amount of electricity, making the operation significantly more expensive. Conclusion. Heat balance is the principle used to calculate turbine power. Isentropic efficiency measures how close the turbine is to its ideal, frictionless performance. Accurate measurement of pressure and temperature is vital for deriving the necessary enthalpy values from steam tables for the calculation. Remember that the turbine doesn't run in isolation. It's one component of the full Rankine cycle, which includes the boiler, condenser, and pump. The thermal efficiency formula shown here calculates the efficiency of this entire cycle. So, while tells us how good the turbine component is, tells us how good the entire plant system is at converting fuel into power. Thank you for your attention. I'm happy to discuss any aspects of this topic.